Hello everyone, my name is Gaurav and today we are going to discuss a topic application of split trees to data comprehension from the subject data structures. The subject code is ACSC08. So here we started. First we should know what are split trees. Split trees are basically a binary search trees that are used to perform some tasks like insertion, deletion, etc. It is not perfectly balanced at all the time. Search and insertion operations are tried to balance the tree so that further operation may run faster. Based on the heuristic, if X is accessed once, it is likely to be accessed again. After node X is accessed, performs playing operation to bring X up to the root of the tree. So do this way that leaves the tree more or less balanced as a whole. Let us see through diagram. Suppose we need to search 12. This is a tree in which this is the initial tree in which we do some operations like zigzag or something we will discuss later, and through the rotations we will get the number at the root number at the root top after doing this playing. So you have got some idea. So playing with 12 makes the tree balance. Subsequent access for 12 will take 0 or 1 times. Active nodes will move towards the root and inactive nodes will slowly move further from the root. So let's see some terminologies in split tree. Let X be a non-root node, okay, and it has and P be its parent node and G be its grandparent node if exists. Consider a path from G to X. Each time we go left we say zig, and each time we go right we say zag. There are 6 possible cases: zig, 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 zag, zag, zig, zag, zag, zig, and zag. When node X is accessed, apply one of the 6 rotation. If single rotation, X has P but not G. This is zig and zag. Double rotation where X has both parent and P grandparent, P and G nodes, in which we perform the operation zig zig, zigzag, zag zig, zag zag. So zig is just a, so we will now see zig operation. In zig operation, zig is just a single rotation as in the evil trees. Suppose 6 was the node that was accessed using search. This is the parent node. Now performing the zig right, which moves 6 to the root, can access 6 faster next time. Notice that this is simply a right rotation. Zig zig operation. Zig zig consists of 2 single rotation of the same type. Suppose 3 was the node that was accessed using the search. Due to zigzags playing, 3 has bubbled to the top. After it again zig, etc. So this is the root. Due to zigzags playing, 3 has bubbled to the top. Parent grandparent is rotated first. So zigzag operation. Zigzag operation consists of 2 rotation of opposite type. Suppose 12 was the node that was to be accessed using search. Due to zigzags playing, 12 has been bubbled to the top. First we did zag left and zig right. So this is simply a LR imbalance correction in AVL trees terminology. First a left and then right. Zigzag operation. In zigzag operation, two rotation of opposite type. Suppose 17 was the node that was accessed using search due to RL imbalance correction. First a right rotation and then a left rotation, through which we access 17 to the top. Zag operation. Zag consists of two single rotations of the same type. Suppose 30 was the node that was accessed using the search. Due to zag splaying, 30 was bubbled to the top. Grandparent is rotated first. Zag operation. Zag operation is just a single rotation. Suppose 15 was the node that was accessed using search. Zag left moves 15 to the root and can access 15 faster next time, O1 time complexity. Note that this is simply a left rotation. Splay trees example. Splay tree, let us see one example. Suppose we want to access 40 using this search. We performed zig operation and 40 splayed to the top. Similarly, if we want to access 60, we did first left rotation, right rotation, and it is 60 is also bubble to top using zigzag, and after zigzag we did zag operation. So what happens when you access 7? How many rotations are performed in all? We have to do. So splaying during other operation. Splaying can be done not just after search but also after OR before other operations such as insert but delete. Insert X. After inserting X at a leaf node, splay X up to the root. Delete X. Do a search on X and get X up to the root. Delete X at the root and moves the largest item into the left subtree. It's a preceder to the root using splaying. Note on search X. If X was not found, splay the leaf. Note that the search ended up with the root. So what we learned, we will see it. Splay may be called before insertion as first splay, then insert. Splay may be called before deletion. So we can use it in insertion and deletion. So why splay tree works? It is because it has maximum height. Splay tree average node depth increases by about half. It is increase in balance. It reduces the real cost. In both cases, splaying improves the performance of the code. So now we'll see what is data comprehension. Data comprehension is the process of encoding, instructing, or otherwise modifying data in order to reduce its size. Fundamentally, it involves re-encoding information using fewer bits than the original representation. Comprehension is done by a program that uses functions or algorithm to effectively discover how to reduce the size of the data. For example, an algorithm might represent a string of bits with the smallest string of bits by using reference dictionary. For conversions between them, another example involves a formula that inserts a reference or a pointer to string of data that program has already seen. A good example of this often occurs with image comprehension. When a sequence of colors like blue, red, blue is found through the image, the formula can turn the data string into a single bit while still maintaining the undergoing information. So application of splay in data comprehension. Suppose we want to compress data over a small alphabet. Prepare a binary tree containing the items of sigma at its leaves to encode a symbol X. Traverse the path from the root to X, splitting O, and go left and 1 when you go right. Splay at the parent of X and use the new tree to encode the next symbol. See, we can see the example. This is the tree. and the example of data comprehension via split tree. So, with this, I would like to conclude the topic. Hope you like it. Thank you.